Today, we're going to focus on analyzing graphs in terms of their maxes, mins, increasing, decreasing, and their concavity. On the handout I gave you after yesterday's quiz, I basically wrote down everything you can possibly imagine about this chapter. The one thing I want to stress is that everything we do today, you already know in terms of your skills. So, before you see the next two problems, make sure you read the front of this page and the back of this page. And obviously we'll go over questions tomorrow. The basic goal for today is to analyze graphs. We want to basically find out everything we can possibly find out about these graphs in terms of their structure. So let's start off with a very simple polynomial function. Let's let an example 1, f of x equal to 4x cubed minus 9x squared minus 12x plus 3. In order to determine whether it's increasing or decreasing, we first set the derivative equal to 0. So you get 12x squared minus 18x minus 12. By setting it equals to 0, you're finding the critical points, as on the cover sheet of your worksheets. The critical points are where the derivative is equal to 0 or where it's undefined. In this problem, the derivative is never undefined, so we don't have to worry about that case. In other words, the critical points are nothing more than the possible values for your maxes or mins. We can then factor this, and when we factor, we get 6 times 2x plus 1 times x minus 2 equals 0. So x equals negative 1/2 and 2. The next thing is a sign analysis. You must keep your sign analysis organized. I'm going to label this as f prime because we're going to have 2 of these for every problem. Next thing, I'm going to put my zeros on there. And make sure you write above it a 0 to indicate that the derivative is equal to 0 at those points. We then plug in for the sign analysis, and we get positive, negative, positive. If the derivative is positive, f is increasing. If the derivative is negative, f is decreasing. And if the derivative is positive, it is increasing. So we now know that this is increasing from negative infinity to negative 1/2 and 2 to infinity. Notice these are all open intervals. There's no brackets here because at negative 1/2 and at 2, it is 0, not positive, not negative. It's decreasing at from x equals negative 1/2 to 2, and you have a max at x equals negative 1/2 and a min at x equals 2. So that's the first part of the problem. The second part, we do the exact same thing again, except now with the second derivative. The second derivative tells us how the rate is changing, in other words, how the derivative is changing. In other words, it goes back to the question, increasing at an increasing rate or decreasing at an increasing rate, and so forth and so forth and so forth. So the second derivative gives us concavity. If we take the second derivative, we get 24x minus 18, which equals 0. Again, we have to check whether this is 0 or undefined. In this case, the second derivative is never undefined, so x equals 3/4. We perform another sign analysis, this time using the second derivative. We plug it in, we end up getting negative and positive. Just to reiterate, this is the second derivative, therefore this negative sign means that the derivative is decreasing. In other words, a decreasing rate. Or this positive means that the derivative is increasing, or in other words, an increasing rate. This tells us about the original function f, and that when it's negative, it is concave down, and when it's positive, it's concave up. So this is concave down from negative infinity to 3/4, and concave up from 3/4 to positive infinity. The inflection point is at x equals 3/4. Basically, the inflection point is where it changes concavity. It can be treated similar to the max or min of the initial derivative. It works the same way. If these signs do not switch, then this would not be an inflection point. And that is the overall structure of every single problem that we're going to do. So we're going to do one more problem. We're going to spice up a little bit. So for example 2, let's do f of x is equal to x to the 4/3 plus 4x to the 1/3. Just to reiterate, the concept is very simple. We take the first derivative, we take the second derivative, and we just simply do our sign analysis to analyze everything. But what becomes difficult about this chapter is the algebra, and these curves get nastier and nastier. So let's take our first derivative. Our first derivative is 4/3 x to the 1/3 plus 4/3 x to negative 2/3. Let's set this equal to 0 and see when it's undefined. I did these problems last year for this exact reason. It is optimal to factor out the lowest number you have, the lowest power of x, which is x to negative 2/3. Now be careful. The second part, that cancels to give you plus 1. The first part here, when you divide them, you get 1/3 minus negative 2/3 to get x to the first. When in doubt, just check your answer. If you multiply x negative 2/3 times x, you get x to the 1/3. It checks out. This part says x equals negative 1 is when it's equal to 0. Be careful. This part over here is never equal to 0. This is a negative exponent. It is 4 over 3x to the 2/3. Therefore, this is undefined at x equals 0. Both are critical points. Both are critical points because one is undefined and one is 0. So now let's do our sign analysis. We plug in 0. I'm going to notate it as undefined. And plug in negative 1, we get the 0. When we plug in values, notice that this is being squared, so this whole term is positive. So I don't even have to worry about this term when I plug in for my sign analysis. If you plug in 5, 5 plus 1 is 6, so it's positive. When you plug in negative 5, you get negative. And when you plug in negative 1/2, you get positive. Therefore, this is increasing from negative 1 to 0, and then 0 to infinity. I cannot stress enough that these must be separated. At 0, it is neither increasing nor decreasing, it is undefined. It is decreasing at negative infinity to negative 1, and you have, if I draw this out, a min at x equals 1. Negative 1, sorry. And a max, never. That's your first derivative analysis. Your second derivative analysis is take the derivative again. You get 4/9 x to negative 2/3 minus 8/9 x to negative 5/3 so it equals 0. If you do exactly the same as we did last time and pull out the 4/9 x to negative 5/3, you get a minus 2 back here. That's the easy one. Here, be careful. Negative 2/3 minus a negative 5/3 is x to the first. Double check it, multiply, you get that answer. So again, you have x equals 2 here, and undefined at x equals 0. So let's do our sign analysis one more time. We have 0 is undefined on the second derivative, and 2 is a 0. Notice this can be positive, negative, so you have to be careful with that. You plug in 5, it's positive, positive, positive. Plug in 1, that's positive, negative, negative. Plug in negative 1, negative, negative, positive. So it's up, down, up. So now, to summarize, we have concave up from negative infinity to 0 to the positive infinity, and concave down from 0 to 2. Inflection points at x equals 0 and 2. Now I want to double check that. The only way a max or a min or an inflection point ever exists is if the derivative is equal to 0 or undefined, and they exist in the original function. I'm worried about the zero, since it was undefined in both derivatives. I'm worried that it may not have been defined in the original function. If the point never existed, it cannot be an inflection point. But when I plug 0 back up in the original, you notice you get 0 plus 0 equals 0. It does exist. Therefore, that is an inflection point. It does work. For homework tonight, you have, on worksheet 1, numbers 1, 6, 7, 12, 15, 33. These three problems are going to be doing exactly the same thing we just did. On 1, 6, and 7, they simply give you a graph and you must find out whether it's increasing, decreasing, concave up, concave down, depending on the question. I stress this. People who don't make mistakes on these problems are those who do a sign analysis. And that's my tip to you. Perform the sign analysis and write your answer, because those people usually do much better on those kind of problems. So do this tonight and questions tomorrow, and we'll clarify anything that was not clarified on this video. See you tomorrow.